Okay. So there is quite a bit of additional information in the new Chapter 7. And quite a lot of that is applied info that I think would be useful. So I'm going to have to carry Chapter 7 over and get it finished after spring break. And then we have a new chapter that I need to prep over spring break on exercise and the immune system. So I'm hoping that I don't have to add a day in and that I can get Chapter 7 finished and Chapter 9 started and not have to bump the exam because we're really tight for time this semester. To get everything in. So that's my plan. I'm going to keep going with the information that I normally cover on Chapter 7, and then there's a little bit of new info on bronchospasms that I can get done today, and then the training and adaptation stuff we'll do. Certainly the training stuff we'll do after spring break. Okay. What else did I need to mention there? Keep your portfolio calendars going, right? So keep a record of your aerobic work that you're doing. Maybe over spring break you'll be able to add some extra aerobic exercise or physical activity things in, maybe go for a hike up in the mountains or something like that. That would be fun. Yeah, I think that's okay. So let's continue here. This one. All right, so I think this is the slide that we were on when we stopped on Wednesday. We were looking at the... Uh-oh. That was weird. The equation VE equals VT times F. Remember, that's like saying the exact same thing, but for air rather than blood that we had with the Q equals SV times heart rate. Okay. For sedentary people at rest, their VE is about 8 liters per minute on average. And that can go up to about 113 liters per minute with activity. If you look at someone who is a trained endurance athlete, then again, rest is going to be the same idea as Q, right? At rest, I don't need to see a difference because we're not doing any work, right? So VE is 8, again at rest, but can go up as high as 183 liters per minute for a trained endurance athlete, long distance athlete. And that's partly because of genetics. It's one of the genetic abilities they have that the rest of us don't have. And that's why they're really good at endurance work. And it's also due to the training, the adaptations that they see. Okay. When we look at the frequency and depth of breathing when we start to be active, so this is an acute adaptation to being active. The first thing that happens is we start to breathe more deeply, right? So we take a deeper breath, and that brings more air and therefore more oxygen in, right? And then if that doesn't meet the oxygen requirements that we need, then we'll start to breathe more quickly as well, right? At high intensities, we start to breathe a lot more quickly because the depth of breathing, the tidal volume plateaus out. And so the only way to get more oxygen into the system when we're working very hard is to breathe more rapidly. Right? Okay. So that elevated volume of air and ventilatory equivalent is called hypernia. And I'm not totally convinced I'm saying that correctly, but I think it's hypernia and that middle P is silent. I could be wrong there. So hypernia is that breathing more deeply, breathing faster. And if you have asthma, then that is going to exacerbate some of the problems that you have. Also, if you have COPD or any other lung diseases, then that can make your symptoms worse. It was called exercise-induced asthma, but now, according to the new edition of the book, it's more commonly called either exercise-induced bronchospasm or exercise-induced bronchoconstriction. And there's a good picture of what that might look like on page 194. Okay? And so some of the symptoms there are that it gets much harder to breathe, and it can become very painful. This is due to the, not excess, but the additional volume of air that's passing backwards and forwards across the membranes, and so that's drying them out a little more quickly and things like that. So it's not as much to do with the allergens now as it is to do with the exercise and the hypernia. Wheezing, coughing, and excess mucus production can occur after the end of the exercise session. And so what they think happens there is that with the constriction comes some inflammation, and we get inflammation, and then the inflammation causes mucus build up over the end of the training session and then into the rest phase. Okay, so about somewhere up to 20% of individuals who are clinically diagnosed with asthma without exercise involved, right, they have asthma, are going to have this problem. But what I found really interesting that I didn't know is that somewhere between 30 to 70% of elite athletes also suffer with EIB. So athletes who are in endurance sports or aquatic sports or winter sports like cross-country skiing or snowboarding, ice skating, those kinds of things. And as I said earlier, the symptoms are more pronounced following the activity, particularly that it seems like the mucus buildup, and they think that's due to an exaggerated parasympathetic response to bring the breathing rate back down, kind of, so during during activity, sympathetic stimulation will bronchodilate as best as it can, right? And then when we stop exercising, it's the parasympathetic system that's responsible for bronchoconstricting back to resting. But what the research is suggesting is that actually it goes too far and it makes the bronchioles very tight. And then we get this mucus buildup and yeah, not very nice. So the suggestions to try to minimize this bronchoconstriction is that it's really important to warm up well ahead of time at a moderate intensity, at least 15 minutes or so, right? Ahead of the competition or the workout. And then to try to minimize this exaggerated response, they are recommending that you do a good post cool down. We should be doing cool downs anyway. It's just typically, certainly I'm guilty of this, but a lot of athletes are guilty. We're very good at warming up ahead of time, and then we finish our exercise session and we go, oh, okay, now I've got to go do, and we don't take that 15 minutes at the end of the exercise session to do a proper cool down. And so they're suggesting that if you have this problem, that's an important element to include. If you're exercising in a cold condition, wear a scarf. Who needs to? We're all wearing masks right now over your mouth and nose, so that keeps the tissues warm, and also will also add moisture to the air that you're breathing in, because it'll get caught in the fibers of the scarf or the mask. Right? And then for some people it may be necessary to take like an inhaler ahead of warm-up. So usually inhalers take anywhere from 10 to 20 minutes to kick in. So you have to remember to take them that much in advance, so that when you start warming up and start to be physically active, they've had a chance to help with the bronchodilation. Any questions? I thought it was a really, it was a really interesting addition to this chapter, because they have mentioned very briefly about exercise-induced asthma before, but particularly this issue of the elite athletes, I think, is just something that I was not expecting. It caught me by surprise when I read that. So, okay. All right, so we've done the breathing bit. We've got the air into the lungs, okay? Now, we've got to get the oxygen out of the lungs and into the mitochondria so that we can use it to make ATP through aerobic metabolism, right? So that's a big old journey that we've got to work out how that occurs. Right, so remember that we've got this massive surface area of the alveoli, right? So that makes diffusing the oxygen across to the bloodstream much easier. We've got that very, very thin membrane that it has to cross out of the lungs and into the capillary, into the bloodstream. And we've got our pressure differences, right? So we have our high to low physics law coming into effect here with gases rather than liquids that we saw in the previous chapter. Right? So if we look at this diagram here, then in the atmosphere, and this is at sea level, partial pressure of oxygen would be 159 millimeters of mercury, right? And in the lungs, in the alveoli, the partial pressure of oxygen is on average about 105 millimeters of mercury. So we've got a pressure gradient there that makes it easy to get oxygen into the lungs, right? We talked about that on Wednesday, I think. So, it's in the lungs, we've got to get it into the bloodstream. So again, the pressure gradient, the difference in the pressure between point A and point B is what's key. And it's going to move from high to low. So when we look at the blood that is coming to the lungs from the right ventricle, right? At this point, the oxygen saturation is pretty low because it's been used by the tissues as the bloodstream moved around the body, right, before it came back to the heart. So when we look here, we've got a partial pressure of oxygen that is 40 millimeters of mercury coming in, and it's going to interact with the membrane, and the other side is 105. So we've got a very steep pressure gradient here, okay? That makes it very simple for oxygen to move out of the lungs into the bloodstream. And when we look at the blood that is leaving the lungs and going back to the left aorta, we see that the oxygen is 100 millimeters of mercury instead of 40 that it was coming in. So we picked up a lot of oxygen here. Uh-oh, what's that all about then? Okay, so we've got 40 coming in, we have 100 when we leave. So that means that we've picked up a lot of oxygen onto the hemoglobin, right? We take that round to the left atrium, it gets squished to the left ventricle, and then the left ventricle is responsible for contracting and pushing that blood out through the aortic valve and off around the body. Right? So we covered all that in the previous chapter. So when we leave the left ventricle, we haven't used any oxygen, remember, while the blood is inside the heart, because it relies on its own external blood supply to supply the muscles of the heart, so it doesn't take oxygen from the blood that's inside, right? So that means that we still have a partial pressure of 100 when it leaves the left ventricle and goes off around the body, all right? So go arteries, arterioles, and then we go to the capillary network. We're going to assume, because of what we're interested in, that this capillary network is wrapped around muscle tissue, okay? And at this point, as we looked at on Wednesday, we get oxygen diffusing out of the blood in the capillaries into the lung tissue in the alveoli. And so then as the capillary network comes together into the vein, we're back down to our nice low oxygen level because lots of oxygen diffused across into the muscle tissue. Okay? So let me do a little diagram. Ooh.
That's right, I can hear something.
Looks as though I got. Hello.
Hello, I can hear you.
You can hear me now?
Yeah.
Okay, I think so. I think they've been having issues with the network on campus today. And
Oh,
I got kicked out. That was not, and I wasn't kicked out of Collaborate, so I didn't know, but yeah, my video and my mic were both shut off. That's so weird. Okay, all right, give me a yell if it happens again, okay?
okay.
All right, where was I? Okay, I was going to draw you a little diagram. All right, so this is the silly way that I remember the law high to low, right? And it may or may not help you, but it helps me. So I'm gonna. Okay. So here we go. If I park my car at the top of a steep hill, right? We're gonna say the car is the oxygen molecule at the moment, right? So if I park my car at the top of a steep hill and I take the handbrake off, what's gonna happen? What's going to happen, Kevin, if I park it at the top of a steep hill and I take the handbrake off?
Yeah.
No, he told me.
Can you repeat it again?
Sorry?
Can you repeat it again?
Sure. So I'm going to park my car at the top of a steep hill, and now I'm going to take the handbrake off. What's going to happen to the car?
I'll probably say like the car was like rolling down. Like,
Yeah, right. It's not a trick question. The car's going to roll down the hill, right?
Yeah.
If it's a steep hill, is the car going to roll fast or slow?
Fast.
Right, okay. So that's point A, right? This time, I'm going to park my car on a bit of a slope, and I'm going to take the handbrake off. So what happens this time?
It'll still go down, but like just slowly.
Right.
Like a bit more slowly.
Excellent. Good. Okay. Third scenario. I park my car on a flat surface and I take the handbrake off. What happens?
It's not going to go anywhere because it's on an even surface.
Excellent. Okay, perfect. So now we have to remember that the car is a gas molecule. So it's either going to be oxygen going in one direction or it's going to be carbon dioxide coming in the other direction. Okay? So we have to remember that the pressure gradient equals the steepness of the hill. The steeper the pressure gradient, the more easily, the faster the gas can cross the membrane, right? If the pressure gradient is less steep, doesn't mean the gas can't cross the membrane, just means it can't move as quickly as it could before. But as long as there's a pressure gradient, as long as there's some kind of angle on the road, the car is going to move downhill, right? If we get to a point where the pressure gradient is exactly the same on both sides of the membrane, then the molecules cannot cross the membrane. They can't diffuse across. There has to be a gradient there. Does that make sense?
Yeah, I think so.
Yeah? So, for oxygen, if you look back at that diagram, right, for oxygen to move out of the alveoli and into the bloodstream, there has to be a gradient between the pressure of the oxygen in the alveoli and the pressure in the bloodstream. And if you look at the diagram, you'll see the pressure in the bloodstream is 40 coming in, and the pressure in the lungs is 105. So there's a very steep gradient there, makes it easy for oxygen to move out of the lungs, diffuse across into the capillaries, and jump on a hemoglobin in the blood. Right? That's at sea level. That picture is at sea level, that diagram. Okay. Right? So here we have a steep pressure gradient. When we get round to the tissue, we have a steep pressure gradient, so it's very easy for the oxygen to leave the hemoglobin, leave the bloodstream, diffuse across into the muscle tissue. Right? If we look at the carbon dioxide, remember that when we are making ATP aerobically, our byproducts are water and carbon dioxide. So the more ATP I'm making aerobically, the more carbon dioxide I'm making. We can't use carbon dioxide as humans in our body. So we have to, it's a waste product, we have to be able to get rid of it. All right? And so we see the flip occur. Right? Because we're making carbon dioxide in the muscle tissue, and we don't have very much carbon dioxide in the bloodstream, then the carbon dioxide can leave the muscle tissue, go into the bloodstream, get carried around. When we get to the lungs, the carbon dioxide is quite low, because in the atmosphere there's not a lot of carbon dioxide compared to oxygen. Okay? And it's not a hugely steep gradient, but the gradient is enough for the carbon dioxide to leave the bloodstream into the lungs, and then we breathe it out. So, whilst we're talking about gases here, it's molecules that are in our bloodstream that are moving those gases around the body. So what's happening with the bloodstream across the lungs is an important idea to pay attention to. Okay? So we want to know how easily, how fast is blood flowing from the heart through the lung tissue back to the heart, right, after it's picked up oxygen, And when we exercise, we know we see faster pumping of the heart rate, so we get an increased blood flow around the body and an increased blood flow through the pulmonary capillaries, which enables them to pick up more oxygen as it flows through. Right? The blood pressure in the pulmonary circulation at the lungs is very low compared to the blood pressure when the blood leaves the heart through the aorta and off around the body. All right? So that does two things. It helps with our blood flow, high to low, but it also means that that low blood pressure protects the very delicate tissue of the lungs. Right? It means that they don't get damaged because it's being pushed by this high pressure. Somewhere around 1/4 of a second to get to the point where we have equal oxygen on both sides of the membrane, right? At rest, it's about 1/4 of a second. As we increase blood flow with exercise, then we get a shorter and shorter amount of time to get oxygen across before we get the level playing field. Okay. One of the things that happens in the body to try to counteract the fact that we have less time is that we see dilation of the capillaries, which increases the amount of blood volume going through the capillary at that time. So that slows the blood flow down a little bit. So we've got this balancing game going on between the speed that the blood is flowing through and the volume of the blood expanding to try to slow that speed down, right? Because we don't want the blood flowing through the lungs so fast it can't pick up hardly any oxygen. That wouldn't do us any good, right? That, however, is one of the things that happens with very, very well-trained endurance athletes. Right? Highly trained endurance athletes might see a decrease in gas exchange at very high intensities because they have more blood volume, but they've also got stronger hearts, and so there's a lot more velocity of the blood through the lung tissue, and they might step over that boundary and get to a point where it's going through so fast they don't pick up optimal levels of oxygen anymore. Right? They have more red blood cells than us though, so again the body's always trying to play this balancing game between something that doesn't work to our benefit and tries to balance that out by counteract that by creating something else that is going to give us a benefit. Okay, I need that one to go away, and we're going to switch to this one. All right, so we have our pressure gradient. We've moved oxygen from the alveoli across the respiratory membrane into the bloodstream. Okay. Now we have to get it around to the tissue. Right? So that happens mostly because it's carried on hemoglobin. A little bit of oxygen can be dissolved in the plasma, in the watery substance part of the blood, but most of the oxygen, as you can see, about 98%, is transported on hemoglobin, which is in the red blood cell. Okay? Hemoglobin has 4 iron molecules in it, so it can pick up 4 oxygen molecules per hemoglobin. Okay? When the hemoglobin has oxygen on it, for some reason they had to go over and above and go, that's now called oxyhemoglobin, right? That just means that there's oxygen bound to the hemoglobin. Okay. Deoxyhemoglobin is hemoglobin that is coming around the system, the circulatory system, that doesn't have oxygen bound to it anymore. Okay. So the concentration of hemoglobin, and therefore the number of red blood cells that we have, determines how much oxygen can be transported. And we'll come back to that idea when we look at environmental impacts on physiology and exercise. Okay? So anemia, then, is the term that we use when we are low on iron. Okay? And without the iron in the hemoglobin, it can't pick up the oxygen. Right? So now we have a problem. If we're anemic, we can't transport as much oxygen around the body as we might need. Okay? So that decreases my ability to do aerobic activity. Right? Uh-oh, can you still hear me? No, you can't hear me. Can you hear me again?
Yeah.
Okay, sorry, it kicked out again. So if we're anemic, it severely impacts my ability to do anything aerobic, right? How do we get anemic? Well, the number one issue for anemia across the planet is iron deficiency. So in many parts of the world, that's because their diets are deficient in iron for one reason or another. For some people, it can be that they have enough iron in their diet, but there's something in their digestive system that stops them from absorbing that iron appropriately. And so then they're iron deficient. It can be due to a hemorrhage, so a really bad accident, or for females, if they have very, very heavy menstrual cycles, around that time they can be a little bit anemic. Right? The other time it can occur is during pregnancy, because the body will direct any nutrients, including iron, to the baby that the baby needs. Right? They're going to make sure that the baby's growing brain has plenty of oxygen, and so if mum doesn't counter that, she may end up a little bit anemic. So when we have lots of 98, 99, 100% of oxyhemoglobin, we call that saturation. Okay? So, our friend, the oxyhemoglobin dissociation curve, which is just a horrible name, it's far too many big words, right? So this curve is meant to, it does, you just have to, it's a little complicated to follow, so I'll do my best to explain it. explains the ability to bind and release oxygen at the correct place, right? So if you think about it, when the hemoglobin is passing through the lung tissue, it has to be able to pick the oxygen up at that point, right? And then somehow, when it's at a working muscle, it has to be able to release the oxygen so the oxygen can pass into the muscle tissue. So think, I mean, if I'm down in the gym training, or if I'm out playing a game, which muscle is the working muscle, right? I could be doing bicep curls and the working muscle is here and that needs the oxygen. Or I could be doing calf raises and the working muscle is all the way down here and that needs the oxygen, right? So how is it that that oxygen gets offloaded from the hemoglobin at the correct point in the body? Right? So that's what it's trying to show us. Okay? So here on the x-axis we have the partial pressure of oxygen. You can see that at 100% pressure here we have saturation, we have 100% saturation. Okay? And we can drop the pressure quite some way and still have basically 100% saturation. Okay? When we get round to the tissues, we know that in the muscle tissue, the partial pressure of oxygen is quite low, right? If you go back to that diagram. Okay? So saturation, that steep curve here, represents how easy it is to offload oxygen out of the bloodstream into the tissue, in our case muscle. Right? This graph is actually at rest, so it's telling us that this is the point of saturation in the veins leaving the muscle. This was the point of the arteries coming into the muscle, and so at rest we offloaded about 25, so 85, yeah, because 70 would be about here. So we've offloaded about 25% of our oxygen at rest. That makes sense because the muscles aren't doing very much, right? Our postural muscles are working quite hard. Our heart is doing its resting thing, but it's still having to contract. Okay? So about 25% oxygen delivery at rest. Okay? And here is the oxygen delivery to the muscle tissue. Now, this curve is impacted by several factors. All right? The first one is temperature. And the temperature effect on the curve, if we get an increase in temperature, the curve shifts to the right. Right? What that means, without worrying about the curve, right? We're just going to go, okay, the curve moves this way. What that means is that it decreases how difficult it is to move oxygen off the hemoglobin. So it increases how much hemoglobin is going to give away its oxygen. Well, that's good because we know that when we exercise, the muscles get nice and warm. So by the muscles getting more warm, it increases oxygen delivery to the tissue. Okay. When we get a decrease in temperature, the curve shifts to the left. Okay. And again, don't worry too much about trying to understand the curve, but the concept is important. Okay? Because when it goes to the left, that means that it increases the affinity of the hemoglobin for the oxygen. That means the hemoglobin is going to hang on tightly to that oxygen, and it's going to be much harder to move that oxygen off the hemoglobin into the muscle tissue. So this is one of the reasons why we have to warm up, right? Because if we don't get those muscles nice and warm, then oxygen delivery to the muscle tissue is slower than it needs to be, right? The colder the muscle is, the harder it is to deliver the oxygen. The warmer the muscle is, shifts to the right, the easier it is to deliver oxygen to the muscle. Okay? Now, another factor that impacts the curve is pH. So the acidity, alkalinity situation, all right? So if we increase acidity in the tissue, the curve shifts to the right, and it's easier to deliver oxygen to the muscle tissue. Again, that's exactly what happens when we exercise, right? Even if we're exercising aerobically, there's still that anaerobic glycolysis going on, chugging away a little bit underneath. It's not the predominant system, but it's still chugging away. And so we still see some increase in acidity at the muscle tissue. That makes it easier to feed the oxygen to the muscle, right? If we see a decrease in acidity, the curve is going to go left, and it's going to become harder to deliver that oxygen. Right? So there's a third factor that I'm not going to go into. If you're really keen on understanding endurance stuff, you can have a look at that in the book, but I'm not going to worry about it from our perspective because it's not something we talked about when we did glycolysis, okay? So we're just going to concentrate on the temperature effect and the pH effect, all right? And the big picture is that active muscle tissue has an increase in temperature and an increase in hydrogen ions, and that benefits oxygen delivery. How am I doing for time?
You're there.
I'm there. I'm at time. Okay. So we will pick up here. We've got to talk about and make a much simpler version of this diagram from the book, which we will do. All right, and look at how the oxygen gets to the mitochondria and the control of ventilation. And then we will look at some adaptations, and then this new bit, this respiratory muscle training, because I think that might be quite interesting for some of you who are aerobic athletes in particular. I assume aerobic athletes. I haven't read it yet. So we will tackle those items after spring break. And then we will start chapter 9. Hopefully we'll finish chapter 7 and start chapter 9 in one class. Otherwise, I'm going to have to jig around the whole schedule. So, as I said, I haven't read chapter 9 yet. That's a brand new one, so I'm not quite sure how long it's going to take to get through that. Yeah, that's it. So, have a lovely spring break. Be careful, stay safe. All right, it is not safe to go to big parties indoors not wearing a mask. So don't be doing that. Hopefully the weather will be nice enough that you can stay outside with your friends. Keep your masks on, stay safe. We're doing so well with vaccination and with bringing the numbers down. We do not need to see that picture reverse over spring break because everybody goes and parties. All right, so be disciplined. I know it's rough. It's not a fun year for you guys being in school, but be careful, stay safe, drive carefully, do not drink and drive. And I'd like to see you all back safe and sound on the 22nd of March.